But the economics of development and exploitation present an enormous short-term strain on the world political and banking resources, and you know that was spelled out very loud and clear in the conference in Nairobi. Now, visionary scientists, and I hope I am one of them, tell us that the ideal fuel in the future will be as cheap as water, that it will be non-toxic, both in its short-term and in its long-term effects, and that it will be renewable in that it can be used over and over again, that it will be safe to handle and present minimal storage and transportation problems and costs, and finally, that it will be universally available anywhere on earth where people can live. I think that's true. Now, what is this magical fuel, and why is it not being used today? Well, the fuel is water. It can be used in its freshwater form. It can be used in its saltwater form. It can be used in its brackish form. It can be used in its snow and ice form. Now, where better place to find this kind of water than Canada, right? I mean, it's amazing. When such water is decomposed by electrolytic fission into hydrogen and oxygen gases, it becomes a high-energy fuel with 3 times the energy output, which is available from an equivalent weight of high-grade gasoline. Again, I say, why is water not being used as a fuel? The answer is very, very simple. Because it costs too much with existing technology to convert water into the gases, hydrogen and oxygen. Or to make the idea a little more clear, all hydrogen exists in a bound form. And like a diamond in a rock, you have to chip it out, and it takes energy. And it takes just about as much energy to chip it out as it does what you get out of it. So the net result is very costly. Now, the basic cycle of using water for fuel is described in 2 equations familiar to every high school student, and I'll just read them off. You just take water, add electrolysis, which conventionally, as you all know, is DC current, and it takes about 250 BTUs of energy, which yields hydrogen gas as H2 and 1/2 O2 per mole of water. And most of you remember that 1 mole of water is about 18 grams. Now, this means that it requires 250 BTUs of energy from electricity to break water by electrical fission into the gases hydrogen and oxygen. Now, the other equation says that if you take H2 plus 1/2 O2, and I want to point out for those of you who are not aware of this, that hydrogen is the fuel and oxygen is the oxidant, plus a catalyst will give you water again, and you get a certain amount of energy out, which is about 250 BTU. Now, the interesting thing about that transaction is that the water that comes out, whether you burn the water, whether you use it in a fuel cell, I mean, you can use it in 2 principal ways. You can actually come out with clean water. That is, if you start out with seawater, for example, the end product will be distilled or desalinated water. It takes a little technology to achieve this, but that's the essential idea. So, besides now producing a fuel, you're producing the oxidant, and you're producing a byproduct that is useful. Let's say you're in the Sahara Desert. Well, you can always pipe in salt water from the sea, or you can get brackish water almost anywhere under the Sahara. You can get your energy out of it, and you can get the fresh water. So there are some interesting things about the use of water as a fuel that usually are not considered in the general hydrogen equation. Now, there is something that I don't want to get into too deeply. It's a rather subtle thing in thermodynamics, and we can get a lot of arguments going on this. But some of the outstanding authorities, I cite Penner as an example, say that if you break water by electrolytic fission at what's called isothermal conditions. That is, the water that's produced at one temperature is burned at this equivalent temperature, and then the water is returned to recycle, and it's a closed system. That because such a closed system, and I've done these experiments, I'm convinced the theory is correct, that you can actually get more energy out of the fusion of hydrogen and oxygen as gases than you put in to break water apart into the gases. And calculations show that you can actually get about 20% more out. Now, you have not violated any law of thermodynamics. This is where the big argument starts. Everybody says, well, you violated the second law. The fact is that you have not violated the second law because the extra energy is absorbed from the environment as heat. You can absolutely account for it. And so when you get into, and I don't want to get into any profound physics right here, but just remember that if you have a closed system that does interact with the outside in the way of absorbing heat, if it's an isothermal loop, that you can actually get more energy out than you put in. And most physicists would say, well, if you could get 1% more out, then you would really be making a great contribution than you put in. And under certain lucky conditions, I can't do it consistently, you can get a little more out than you put in. And I'll go into some of the thermodynamics later on, and also how you can profit from that particular peculiarity of the second law of thermodynamics, specifically with respect to water. So if this reaction, which I've only read to you, could be carried out at even 100% efficiency, the release of energy from the reaction where you combine gases to get energy and an exhaust called water, that you could have a net energy profit, which would make the use of water as a fuel an economically feasible source of energy. I'll justify that statement as we go along. To continue in the general line of the philosophy involved here, the cost of producing hydrogen is usually directly related to the cost of producing electricity. Now, hydrogen as produced today is generally a byproduct of off-peak hour electrical production in either nuclear or hydroelectric plants. Now, the electricity thus produced is the cheapest way of making hydrogen. Now, I've used some figures here which are based on pre-1973, that is pre-OPEC price rise figures for oil, because anything subsequently is subject to so much fluctuation it's hard to come out with any comparable estimate. I've also calculated that for the figures from that period, 1973, that my baseline for the cost of electricity, this is just production, is 9.1 mils per kilowatt hour. Of course, it's gone up since then, but all these figures are relative, you'll have to remember. Now, for example, electricity, to produce it, and we're talking now of a unit of 10 to the 6 BTU, a million BTUs. The cost of electricity, just to produce it, is $2.67, US dollars, sorry, I'm in Canada, I forgot, is the baseline. The transmission of that same electricity is 61 cents per 10 to the 6 BTU, and the distribution costs are $1.61, making a total cost of $4.89. The figures from which I obtained this, for those of you who want to follow up, are from Penner's work on Non-Nuclear Technologies, Volume 2, put out by Addison Wesley Publishing Company, 1977. Well, if we compared only the unit cost of production of electricity versus hydrogen from the above table, that is 10 to the 6 BTU of hydrogen versus 10 to the 6 BTU of electricity, and forget transmission, storage, all those things, the unit cost then is about 100 or 20% higher for hydrogen, which is surprisingly, you'd think there would be a higher differential. Now, it must also be noted that the price of natural gas, and I haven't included these figures, but I want to point it out to you, is actually much cheaper than either electricity or hydrogen. But again, because of the price fluctuation due to, at least in the United States, the recent deregulation of gas, it is not possible to present a realistic figure at this time. And those, I don't know what the situation is in Canada with respect to price controls on natural gas, but I suspect sooner or later it will get phase coupled to the U.S. price deregulation thing, and it seems to historically follow that way. Now, in the opinion of Penner and other authorities who agree with him, have I damaged something with this? In the opinion of Penner, if the hydrogen production cost component of its total cost could be reduced only threefold, it would become a viable alternate energy source. Now, in order to achieve such a threefold reduction in production cost, several major breakthroughs would have to be made. One, the endergonic reaction is the amount of energy actually absorbed by water with electrolytic driving to get the gas out. Okay, endergonic for those of you who don't know the term. A technological breakthrough that permits 100% conversion efficiency of water by electrolysis fission into the two gases, hydrogen as fuel and oxygen as oxidant. For comparative figures, for those of you who may not be familiar, the efficiency of DC electrolysis at this time, and again this depends on the method of accounting, and we can discuss that later, is anywhere between 50% to 74%. That's by so-called electrolytic chemistry Faraday law accounting. Number two, you need a breakthrough in hydrogen production, and this is a very key element of my work, in situ. That means a technological breakthrough that eliminates the need and cost of hydrogen liquefaction and storage, transmission and distribution by producing the fuel in situ when and where it is needed. Now let me explain that one point. I gave, as I say, this talk in Toronto, and I think we had very distinguished scientists there, both from the University of Toronto and around the world. And one of the scientists who I have great respect for made the comment to my wife later on that this business of hydrogen is just hogwash because it's too dangerous, it's explosive. I call that the Hindenburg mentality. Now the reason for that is that everybody knows hydrogen is explosive, but it's explosive when you produce it and you compress it and you liquefy and you put it in heavy containers and start fooling around with it in terms of movement. I just want to make it clear that the invention that I have developed, and I wish I didn't have to use the word I, it sounds like an ego thing, totally eliminates that phase of hydrogen utilization. My development actually produces the hydrogen as it is used. There's no storage, there's no liquefaction, there's no transmission. The only transmission is to find water somewhere to pour into your tank. And you do that with a bucket, usually by hand, and does not enter into our thermodynamic equations. The third breakthrough required is that in the exergonic reaction that is using the hydrogen and oxygen, whether you're going to drive a turbine or you're going to make steam out of it or run it directly in a fuel cell, should also be 100% efficient in its energy release. And I'll comment on that later in terms of fuel cells, turbines, and so on. None of them are 100% efficient as far as I know in the present state of art. Number four, engine efficiency. You really need a breakthrough by combining the breakthroughs under 1, 2, and 3 that I've just cited and utilize them in a highly efficient engine to do work. And in my opinion, and I'll try to reason this out with you, it is actually possible to achieve a 15 to 20% surplus of energy return over the energy input. That is in the ideal case, and we're disregarding the actual effect of a load while you're using the hydrogen as fuel. Now, this part of the talk is now technical because I'm going to describe for you, and this is really the first time I'm describing it publicly, because in Toronto we had problems with this kind of projector and so on. I never showed my slides. So here, thanks to Andrew's work, we have a page projector. Now, I think one of the important aspects of this invention, as I just described, is you skip liquefaction, storage, and transmission problems of the fuel. And this alone gives a total cost, both in terms of energy expended. It takes a lot of energy to liquefy gases, as you know, and transportation and other costs. Both energy and cost savings are about 25% immediately. And again, that depends what part of the world you are, how good your technology is, and so on. Now this, I call it a TD device. It's a contraction for thermodynamic. It's based on what I think is a new discovery, because as far as I've been able to establish by a very deep search of the world literature, nobody, to my knowledge, has had an efficient use of alternating currents to get water electrolysis. So that is the novel aspect that I'm presenting to you tonight. Now, I have been doing tests almost for a year repeatedly, and I'll explain how I do the tests, where I can pretty well come to close to 100% efficiency on the average from test to test. I'm always varying parameters, so I never really run the test for pure efficiency because the tests are very costly, and I'll just explain briefly. When I measure how much electricity I'm putting into the thermodynamic device, which I'll show you, I have to have very precision measurement, almost counting for every electron going into solution. When I measure the product, which is hydrogen and oxygen, I have to use very expensive mass spectrometers or gas chromatography equipment, which I personally don't own, because I think, as everybody knows here, I'm a poor researcher, but it does cost me $75 an hour to use these machines, and a good run usually costs me about $1,000. So I'm very careful how I do it, and everything has to be absolutely right. But I do test new parameters every time I make use of these rather expensive machines. So the average efficiency fluctuates around 100%. I do get better, I do get worse, depending on what I'm testing. And again, I emphasize that no laws of physics are violated in this process, because we can account pretty much in a scientific way for every factor in the thermodynamics. I'm going to start putting this on the wall to give you an idea of what we're talking about. Is that visible to everybody? More or less? Okay. This is called component 1. And this is the electrical signal that I generate to break up the water. These are unique circuits. I don't give you the fine details. I have some 61 patents on this particular circuit system, which I've collected all over the world for the last 20 years. But basically, you start at this end. This is a coaxial electrode. Looking down from the top, there's a center electrode here, and there's a ring electrode. Going backwards, we have an inductor in one line, an inductor in another line, and this is called, for those of you who are technically oriented, a series L, that's inductance, C, the C is in this fluid here in the water, series LC resonance circuit, which something that Andrew mentioned earlier, and which was one of the great bases of most of the Tesla circuits. Now over here you have an output transformer, and one of the features that's very important here is that there is a resonance sensing resistor here which senses the current flow through this system and continuously adjusts the frequency of the whole circuit back here to the sample, so that the alternating current is always in pure resonance. Pure resonance means you get the maximum amount of current through the system for the least amount of power. This feature is absolutely essential to 100% efficiency. If you cut out this feedback and cut out the series resonance, your efficiency drops to about a half. Very important feature. The power amplifier is obvious. We have then on the input end here, we have an audio oscillator and preamplifier, and not really shown properly here, but it's in here, is an oscillator which oscillates the basic carrier frequency. And then of course we have preamplifier, and we use amplitude modulation. All this makes a very complex wave, which I'll draw later on the blackboard. So that is component one. This looks very complicated, but for small power applications this can all be reduced to a chip. It's no big deal in terms of it's all state of art. That's the word I would really want to use. Okay, now the next part is what I call component 2.
Oh, that's component 3.
Comes up through this tube to the center electrode and fills this cavity here. So that's step one. I just showed you the electric function generator, which is, its output is across the center electrode, think of it here, and the outer barrel over here. Now, over here, very important feature of the invention is a ceramic coating. And the chemistry of this is enormously complex. But just to give you a simple statement, the field intensity is very high in the center electrode, obvious to anybody who's an electrical engineer here. And the outer side is a low intensity, so the gradient is very high. The gradient actually carries H2O through the pores, there are channels in the ceramic, and the actual breakdown of the liquid of water occurs in the fine channels here. It's a kind of a micro channel solid state system, and then the gas moves up along these channels here and comes out here. I don't want to go into all the details, but every component here, the length of this, the diameter of this, the radius of this, the curvature of the cavity, the lining, it's everything is designed for resonance of the signal that's being used, very much like a microwave cavity resonator. The difference is that the microwave cavity resonator is operating at a very high frequency, and this operates at a very, very low frequency. I use audio frequencies. The center frequency here is approximately 600 hertz with very complex higher harmonics and sidebands, but essentially they're all within the so-called audio range. Now, the reason all this works is because you not only have a very complex series LC resonance operating in this cavity, but because of a magnetohydrodynamic effect, which is very simple and very classical, we actually produce sound waves in here, or phonons as they're called technically. And the phonon is almost as important as the electronic energy in, and I'll show you why later in some diagrams of the water molecule. But I'm just giving you a general rough idea without giving you all the thousands of measurements that are involved in this kind of structure. There's nothing here that cannot be produced, mass-produced, cheaply tomorrow. Now, one more slide about the system. This is the component 3. The component 3 is the actual fluid itself, and it is a whole electrochemical system in itself. There are certain ions that are released from the center electrode, certain ions that are released from the outer electrode. There are certain semi-almost, I can't even find the right words because I don't want to bog you down a lot of chemistry. There are certain chain compounds produced in here which are an important novel feature of the electrolytic process. And that's a whole separate study in itself, the nature of the chain compounds. And the important thing, the bottom line, is that through the sensors that feed the system, you always try to maintain the salinity of this solution, and essentially a sodium chloride, although other ions can be used, at 0.15 molar. That's another important feature of getting 100% efficiency. So anyway, I must just tell you that I'm very happy because I'm about a month away from wrapping up all the basic mathematical and physical and chemical and electrochemical research, and I'm getting ready to go into an engineering phase. So that's the basic system that has been developed. Now, you can perhaps meditate. Oh, here's just a little slide to give you an idea of what I'm talking about thermodynamically. And I think this may clarify a lot. Delta G is something called the Gibbs function. The Gibbs function is essentially the free energy in a system. So you have water here, it takes so much energy, in our case as electricity, and you break it up into gas, okay? And that has a certain value which is given here. Now when you burn or utilize the hydrogen and oxygen here, you then get the formation of water, and you get what's called the enthalpic energy, or delta H, which has a higher value than this one. And this happens to be about 20% higher. And there's a differential in here, which is normally lost in the electrolysis and burning of hydrogen is used today. And I take advantage of this differential to get my high efficiency. But this will show you the way the reaction runs in time and the amount of energy. And this one, again, for those of you who are technical, is the endergonic energy. That is what the system absorbs. And like this, I have these signs wrong. And this is what is liberated, okay? So that will clarify that part. Now, this I'm just going to leave on here until we get to it. And you can think about it, but it's rather obvious. This is the structure of water that people don't really think about when they discuss electrolysis. It is, just to give you perspective, the water molecule is enclosed in a cube, and you have here a perfect tetrahedron, and here is an oxygen atom as the center of mass, and these lines here are vectors pointing to the apices, and this is the hydrogen apex here. This is a hydrogen apex here, and L1 means lone pair electrons. That is, you have 2 electrons here, and you have 2 electrons here. And again, to jump ahead of where I am in the paper, I hope I'm not running too slow. My system, and this is part of a very complicated patent claim that I make, is this, that the normal bond angle from here to here of water is 104 degrees. By pumping electrical energy in both as phonons, that is sound waves, and as electrical waves or electronic waves, I pump up the energy, and there are quantum mechanical rules that describe this, to 109 degrees. I mean, the energy pumps this thing up so it becomes rigid at 109 degrees in 28 minutes. That makes it such a rigid structure that if you hit the resonant frequency, which is what I've done, the thing just shatters apart very easily. And it all has to do with the relationship of the hydrogen here, and I just want to make it clear for those who don't read this directly, is a single proton here, a single proton here, 2 electrons here, and 2 electrons here. So all the physics and chemistry revolves around this structure. And I'll just leave that there while I go on with the rest of the discussion. Now, a little more philosophy before we get into the technical details. For those of you who are concerned about the philosophical side of energy, let me just give you an idea how the overall system works. Now, if you draw a line across here, and I should do so, okay? Let's look at the material above here. When you're looking at this area here, solar, wind, auxiliary, etc., we're talking about what's called free energy. And I know that's a word that's been abused and misused in every way. What I mean by free energy, it's something that falls out of the sky like water or wind or something. You collect it. You're not paying anything for the collection process. You begin paying for the conversion process. The photon comes from the sun, hits your photovoltaic cell. It costs you a lot of money to make the thing, and you've got to amortize it over 20 years or whatever, and you come out with some calculation that tells you how much it costs you per watt or kilowatt hour, etc. Likewise for wind, if you have a wind charger, you're out in the country, and you want to use that as a kind of a free energy that you're going to convert to use in the electrolysis system. And there are different kinds of auxiliary chargers that you can use. One example being that if you're not using hydrogen and oxygen in a fuel cell, or you're not burning it up, why not store it in your own tank without going through a lot of elaborate stuff? And at night, when you're not using the system that I've just described, that is component 1, 2, and 3, you can be charging something. And over here, collected and feed it through component 1 and component 2 into electrolysis, you will put in 1.1 kilowatt hour, and there's a 10% loss at that point with the system as is now, and you'll get a kilowatt out. So that's called 90% efficiency. It's very obvious right there. Now, you can then take the gas output here, for example, and you can get your gas as hydrogen and oxygen, and because of the nature of this conversion process from wind charger to here, and the electrolysis, you get a lower figure, about 0.85, which can be converted into percentages right away. And with an auxiliary charger, because you're dumping into a storage battery, this of course is a fuel cell, you get even a greater loss. So this is the free energy part here, and you can feed it into a water system, either as energy, as coming out as gas, or as a fuel cell. These three sources here, and including an outside source, which is an auxiliary, you can have a steady charge around the clock, 24 hours of half a kilowatt hour. You may have anticipated this, is the water as both a fuel and a storage medium. The water can be used in both senses, and that's the key to this whole idea, is to be able to tap off intermittent, unreliable sources like solar, wind, and others, where, depending on where you are in the world, run the system continuously, even though they are intermittent individually, so you have something going 24 hours a day as free energy, even though you have to pay for it here because you've got it out of here. And then, since most power use in a car is a good idealized model of that, is intermittent, unless you're off on a, this doesn't apply to cross-country truckers. This applies to family use of a car where you go from here to there for an hour or two or three. and therefore you have intermittent use of that vehicle. The electronics is so devised for complicated reasons to resonate over a range of 200 to 100,000 hertz, although nominally, given a whole set of parameters, I operated myself at about 600 hertz. The modulation frequency, which is audio, runs from 20 to 200 hertz. And it's a very important part of the process, as I mentioned, because not only do you have a phonon wave riding on a carrier wave, but you have sidebands which create beat frequency differences. And for those of you who are electronics people, you might be interested. The idealized wave is like this. Out of the component 1 generator comes a sine wave, classical normal sine wave. Everything is designed that way. But when that wave looks into the coaxial cell that I am using here, with the water coming up here, it looks into what's called, those of you engineers, a highly nonlinear load. And this sine wave in a nonlinear load becomes a square wave pulse. But it's not exactly that way, because that would not produce 100% efficient electrolysis. What I get at this point is a very peculiar wave where, let's start here, where as we come over here, this wave resonates in a very narrow time frame, like a microsecond, at very high frequencies. When I say high frequencies, that is, this pulse wave looks like a Fourier transform spark system, and I get frequencies in here weak, but up in a gigahertz range, about 22.3 gigahertz. Now, the most important feature of all is the water solution. Let me get back to it now. The important thing about the water solution, let's see if I can make a little sense of this. From a thermodynamic point of view, an electronic point of view, really quantum mechanical point of view, these vectors are idealized vectors. You don't actually see those in the structure. And these lone pair electrons kind of oscillate out there by so-called hydrogen resonance systems with the hydrogens out here. And this is such a complicated system that it's very hard to go into it in a simple talk. You have to get into computer analysis here to find out what's going on. But in essence, this is a center of mass, and you have resonances from here to the outermost tip here. You have resonances over here, and these are proton resonances, mind you, and these are electron resonances. And the combination of all these at audio frequencies, as I've indicated, and one more feature which I'll now give to you, result in a high efficiency. The last feature, which is a very important part of this invention, is that I increase the amplitude of that wave. Let's say it's a sound wave. It goes up and down from 0 to 90%. In other words, imagine the wave getting larger and smaller, and that is cycled over a certain cycle which I tune to the liquid sample of about 2 to 3 seconds. And what I'm achieving in that slow cycling of energy up and down, and I'll have to show you a drawing, is I am rotating the nuclear magnetic moment of the proton here and the proton here. And it's that action which actually is the final resonant factor which causes a breakdown. Now those protons can be conceived of as little magnets like this, which are flipping over at this cycling rate of 2 to 3 seconds, depending on what I set it at. And just have the lights. Thanks. Now I'm going to go into the rather boring part, and I hope that it will not be too boring because I want to show you how I evaluate the efficiency of electrolysis. And maybe I better do this, skip all the equations here. Let's go back here. We have some kind of auxiliary energy here which we've classified and perhaps loosely as auxiliary energy, and we use solar here. So we have some kind of a collector here, photovoltaic cells, and we have a feed of the output of that either directly back into the electrolyzer, that's component 1, or if we want to do some switching arrangements here, we can dump it into a storage battery, although we lose efficiency when we do that. And as you can see, we have a load out here. And so if we start out and measure the joules, and here's the give function, required to electrolyze a certain amount of water, in this case 1 mole, we then apply it to the water, we have gases produced, and we dump it in this case into a primary battery, which is called a fuel cell. And here are some comparative figures of what you put in and what you get out. And it turns out, and I've done experiments along this line, that you can have something which I don't think anybody's ever developed, and I'll explain this why. You can have a closed system here. And what do I mean by that? I mean that the temperature of the system is constant from here to here to here. Now, why is that important? Let's say it's at room temperature, 25 degrees centigrade. In the normal fuel cell, the way it is done now, you buy the liquefied hydrogen, and under high pressure at very cold temperature, you squirt it in here. Now, before you can squirt it in here, you've got to heat it up. This is one of the hazard danger problems that people talk about. And you have to bring it to a certain temperature, and it depends on whether your battery is a low temperature battery or a high temperature battery. But the whole point is you lose an enormous amount of energy just changing gas pressures and changing temperatures right here. So your efficiency is bound to be low just because of that function. Hydrogen, energy in general, water, something viable for the future. And again, I want to emphasize, most of you know I am a physician by training and in spirit, of producing fuel for this planet that really is non-toxic to humans, that includes mothers and children and husbands and dolphins and plants and everything else, and God knows the list is endless of things that are happening. And I personally feel that our enormous use of fossil fuels with their toxic end product, whether it be sulfur dioxide, which affects biological systems, or the nitrous products which go up and deplete the ozone layer, and a lot of other things that you and I know, some 40 known toxic agents that come out of exhaust emissions. I think if we're going to fall as a civilization, it'll probably be, and I really believe this, from asphyxiation. If you've ever been caught in a big traffic jam in a big city like Mexico City, you'll know that the possibilities of asphyxiation are very imminent. And LA is not far behind, and most of the great cities on this planet are incredibly polluted. The first time I ever learned, and this is just an anecdote, how polluted cities are, I lived for a while in the state of Maine, in a very beautiful primitive area on the sea where the air was literally always fresh, and there was a scent of pine in the air to boot. And I had friends who had a lovely country home, and they had a set of leather-bound volumes of Stevenson, and they loaned me a volume one day to read, which I read, and I had to make a trip to New York. And in New York, they had a penthouse apartment right in the 50s on the East River, a very posh townhouse, and they had left the other half of this set of leather-bound volumes in New York City. One had been in the fresh country air for 10 years, and the other had been living in New York City for 10 years. The leather in New York City just crumbled when I took it off the shelf. It had been totally eaten up by the sulfur compounds in New York City. I might add that the Con Edison plant below at UN was only about 12 blocks away. But that really impressed me about, and then of course working at New York Medical Center in pathology and cardiac surgery, etc., I have seen endless black lungs from people who've lived there all their lives. And I'm just aware by the feel and the smell and the sight and the sound of how really corrupting pollutants are. So my real interest, and if this thing ever succeeds, and we know there's no guarantee with all the competition from other sources of energy, especially from gas pumps, whether it'll ever succeed, but I just want you to know that my real motive is to somehow get clean air into our lungs and get where we're going without paying a little asphyxiation price on the way. Thanks a lot.
So, any questions? You put into the storage battery is greater than what you would get from
60% efficient, as I've shown. In other words, if you put in, so it's more efficient to go from the photovoltaics, where when you come out, you still have 100% of the energy, and you could burn it directly, for example, which is very efficient. It's an idea that people have not thought about, and therefore it may be a little foreign. But if any intermittent, and I made this point before, but I'll repeat it, you could cheat a little bit, have the sun hit your photovoltaic cell, a lot of heat is lost. You could have water coolers, water circulators there. I have not concentrated in this talk on explaining thoroughly and in depth, point by point, how you can actually conserve energy by the storage medium you use. If you do have the energy stored, so the trick is to unlock the key and get it to come out as cheaply as possible.
Dr. Puharich, up till now, energy experts have characterized hydrogen-based energy as essentially a non-starter because of certain efficiency losses in terms of the conversion through electricity into the generation of hydrogen. Could you elaborate a bit on what caused those efficiency losses and how your theoretical and practical work has seemingly overcome those efficiency losses and rendered hydrogen a viable energy source?
Okay, the method of producing hydrogen from water up to now has been like hard rock mining. You literally hit the water molecule with a big club, and it takes a lot of energy, and you always get less out of this thing you've broken than you put into it. And this is known, and this is what you've stated. But there are methods which everybody recognizes in principle. It's the old story of the marching of the soldiers marching over the bridge. If they all get in step, they cause a series resonance of the thing and it breaks apart. So if you jiggle a water molecule by resonance principle, it falls apart easier, it takes less energy, and therefore what you put in you can almost get out. So what I've really done is gone from ordinary direct current, which is like the club, hitting the rock, versus the gentle tickling or the opera singer shattering the glass of water, as we've seen so many times in television commercials. So that's the central idea. Mm-hmm. And this gives you almost a doubling in efficiency and increases the amount of recoverable energy. The other thing that I've done, which is well known, it's nothing new, I've really not contributed here, is you want to capture as much free energy from the sun, the wind, hydroelectric, wherever you can capture, and there are a lot of sources, thermal, etc., to feed into your electrolysis system on a small scale. I'm thinking of powering cars, I'm thinking of heating the home, electricity for the home, hot water heater, that sort of thing. So the more, well, if you capture that free energy, in essence, you can beat this no-win situation. You can actually get more energy out than you really put in, because the extra energy is free energy, so-called.
Mm-hmm. In Canada, we're blessed with an abundance of hydropower in the form of highly centralized high output energy grids. And I was wondering, to what extent is this technology adaptable to a highly centralized hydropower grid system, such as the one we have here in Canada?
Well, what I would advocate, again, this is a matter of philosophy, is to shoot for a decentralized production of hydrogen through water. Essentially, think of every home as having a little plant, let's say 10 kilowatts, that heats the house, heats the water, does the air conditioning through, certain cycles, and produces the electricity for illumination. And what you would do there is you would utilize the sun that you capture with photovoltaics, wind power, small windmills where people used to have, and other sources. And if you have surplus power, you dump it, as they do in Wisconsin in the United States, into the grid, the local grid system. And when you need power, if all of the sun and wind fail, then you cancel the costs of the two against each other and pay the difference, if there is one, to the local grid. Now, the big thing and the important thing to address directly to your question is storage of these intermittent energies like thermal, solar, and so on is a big problem. Mm-hmm. And the greatest storage system in the world is a hydroelectric system, because the sun lifts up enormous amounts of water, transports them for free, dumps them in your reservoir, and they just sit there ready to be tapped. So in off-peak hours, you can be producing hydrogen for different kinds of use. For example, feedstock in the petroleum industry, you need a lot of hydrogen to do various things, to hydrogenate various carbon compounds. So a lot of the stored water energy can be diverted toward producing feedstock, and your local intermittent solar, thermal, wind, so on can be used to produce local energy. And the last part of the idea is that people have really got to start thinking low energy, small, and so on. I mean, we're living in a fool's paradise. We're burning lights and fuel, natural gas, oil, as though it's going to go on forever, and we know it can't last forever. We are depleting all the future resources of this planet, and really it's very unfair to future generations.
Mm-hmm. As Buckminster Fuller says, we're living off our energy savings account instead of generating new energy wealth.
Yep, exactly.
I imagine, well, the developing world obviously presents a whole different set of problems and opportunities for this kind of technology, and I was wondering if you could elaborate on some of those problems and opportunities.
Well, those problems are very apparent. I've lived in most of the, for example, underdeveloped countries of the Western world, Central America and South America. And the problem there is very simple. There are little farms scattered all over the bush that never see an electric power line, and they need some kind of energy to pump water up. I mean, if they had a good pumping system, they can somehow afford as a community to punch one well down, by just taking a collection from everybody. Small power units in other countries like tractors and so on are becoming, not particularly Mexico of course, but Brazil as an example, are becoming almost impossible economically because of the high cost of fuel, hydrocarbon fuel. And countries like Brazil, of course, are experimenting with alcohol. So I think there's a much greater need for small power plants that can produce electricity, turn wheels, and heat water, et cetera, than there is in our, more developed, more abundantly gifted countries.
Mm-hmm. What has been the initial reaction of the scientific community to your discoveries in terms of enhancing the efficiency of hydrogen recovery?
I would say very skeptical, simply because the efficiencies just don't fit the preconceived standard model of what you can get out of hydrogen. But this is the first real full discussion I've given about my work publicly at this meeting in Ottawa. And I would say only that any scientist who has worked with me in the laboratory and has seen my results firsthand are very enthusiastic. But when they just hear about it verbally, they know it can't be so. And I'll have a little bit of a problem, I think, getting that point across.
And working up the papers for the journals.
Right.
Thank you very much, Dr. Puharich.
Well, thank you very much, John.